Ron is a distinguished engineer at Juniper with the focus currently on IPv6 and segment routing. He has been an AD in Ops and Management area in the past, and currently a working group chair in V6 Ops and OPSEC working group. His talk today will focus on IPv6, starting from the history part and the current deployment and future plans in IPv6. So off to Ron.
Hello, good to join you all. I apologize for the problem for the late start. I'd like to talk a little bit today about IPv6 past, present, and future. And the first question is, why is this an interesting topic? Well, the history of IPv6 is a bit interesting. There were some good stories about people who were the founding fathers of IPv6. That might be kind of interesting. The present is kind of interesting. But what's really interesting is the future. And to understand where IPv6 is going, we need to understand where it's been. So, let's dive right in. And we start before the dawn of IPv6. We're talking about 1981 through 1994. Now, I can't see you, so I'm going to ask for Drew or Reggie or somebody to relay the answer to this question. The prehistory starts in 1981, when the IPv4 spec was published. That's RFC 791. Now, I'd like you to raise your hand if you were working in 1981. Drew, how many hands do we have?
One hand up. One hand up. One hand up.
One hand up. One hand. And that's probably Adrian Farrell.
Adrian is more like baby.
I'm sorry, I didn't hear that. Okay, let me ask another question. How many of you were alive in 1981?
Lots of hands.
How many hands do we take?
Lots of hands. Lots of hands.
Okay, good. So I don't feel like a total dinosaur. Okay, so IPv4 starts in 1981, and there's a magic number. The magic number is 4,294,967,295. That magic number is, strangely enough, equal to 2 to the 32nd power. Now, what is that magic number? Well, it's roughly equal to the number of people alive in 1981. And it's exactly equal to the number of IPv4 addresses. And there's an anecdotal story. I don't know if it's true or not. I heard it from Dave Russell, who at the time was VinServe's boss. And they were trying to figure out how many IPv4 addresses there should be. How wide should the address space be? And they basically said, there are about 4 billion people on the planet. There will never be a time when there'll be more IP connected devices than people. So 4 billion should be enough for all of eternity. Little did they know. Well, anyhow, their guess was roughly correct back in those days. Relatively few people were connected to the internet in the beginning. There was ARPANET, there was NSFNet, there was NERIT. People were grabbing big blocks of address space. They were grabbing /8s, even though they didn't need them. But there was no reason to believe that IPv4 address space would ever run out. Well, then something happened. The internet went from being a science project shared by a few researchers in the U.S. Department of Defense. It went from being a science project to a social phenomenon. Beginning in about 1992, you could buy dial-up access to the internet. Anyone could buy it. And in America, the first service I remember was AOL. And soon after that, there were always-on services. Well, once internet access became ubiquitous, IPv4 address started to be consumed very quickly. Some people took a look at the rate of consumption And they predicted that IPv4 address space would run out in 2010. And those predictions, as we'll see, were pretty close to being correct. So people started coming up with mitigations. The first mitigation was classless IP addressing. Now, most of you, when you look at this, will scratch your head and say, what's that? Because you don't remember classful IPv6 addressing. Once upon a time, there were only 3 subnet lengths in the internet, /8, /16, /24. The first 2 bits of an IP address told you whether the address was drawn from an 8, a 16, or a 24. Well, they came up with this classless IP addressing, which is what you know and love now. The other thing they came up with was private addressing. You know it well. If you look at the address that your laptop has in your house, it's probably 192.168 something or other. That's a private IP address. The reason private IP addresses work is because we NAT them. You're probably all aware with that. But sometime around the middle of the 1990s, we started to realize we were going to need another version of the Internet Protocol. Now, this is amazing. The Internet Protocol had only been specified in 81. It only started to get wide deployment in 92. And by 93, 94, we knew that there would have to be a next generation of IP. And it started out in the IETF as the IPNG working group. And this brings us to the dawn of IPv6, 1995 through 1999. Well, the IPNG working group worked for a while until it came out with RFC 1753 in January of 1995. So most of its work was done in 93 and 94. Well, there were many proposals about what the next generation internet would look like. CatNav and SIP and Tuba. But finally they landed on what a precursor of what we call IPv6. It had 3 salient features. Big addresses, extensibility in the form of extension headers, and auto-configuration. Excuse me. It was more than IPv4 with big addresses. It also gave us a first good look at the IPv6 header as we know and love it today, extension headers as we know them today, and address auto-configuration. And what's amazing is, if you ever get a chance, take a look at RFC 1753. It looks surprisingly like RFC 8200, the current IPv6 standard. In the 20 some odd years that elapsed between 1753 and 8200, not a whole lot has changed. Well, RFC 1753 gave us an idea of what IPv6 would look like. We finally cranked out real specifications at the end of 1995. There was RFC 1883, the IPv6 protocol, the addressing architecture, 1884, IPMPv6, v6, 1885, neighbor discovery in RFC 1970, and SLAC in RFC 1971. So it's probably worth reviewing those for a little bit. The IPv6 specification told us what the header looked like. It told us how the header was processed. It explained extension headers and how they're processed. The addressing architecture told us what an address represented, that is, an interface. And it started to talk about the difference between the high and low order bits of an address. IPMPv6 was, pretty much an extension of IPMPv4. ND and SLAC we'll talk about in a little bit. Well, these standards remained in place from 93 95 to 98. Still, there was almost no deployment. Between 95 and 98, if 0.001% of internet traffic was IPv6, that was a lot. But during those 3 years, all of the graphs that we talked about got updated. 1883 got replaced by 2460. The ND spec got replaced. Everybody on the list, you'll say, was replaced. But there were some things that were really interesting in those old addresses. First is we came up with a really big address, and we chose 128 bits to be the address space. Now, 128 bits is a really big number. I can't tell you if this is true or not, but the anecdote that I've heard is that if you got 2 to the 128 peanut M&Ms, you could fill up Lake Michigan with them. Now, I'm afraid I just told a culturally bound story. A peanut M&M, in case you're from someplace where they don't have them, it's a peanut that's covered in a chocolate and sugar shell. So a peanut M&M is about twice the size of a peanut. And, you know, if you got 128, 2 to the 128 of those, you could fill up a lake that is, roughly the size of England. The other thing, so it's a big address. Now, it really isn't that big, because the high order 65 bits identify subnetworks. And there's a strong recommendation that the low sort 64 bits are a host identifier. So the recommendation is that every subnet is a /64. But still, 2 to the 64 is a really, really big number. It's 16 billion billion. The address size is 4 billion times the IPv4 address size. The next thing is they introduced address types. And address types don't map exactly to IPv4 address types. Global unicast maps to IPv4. There's a global unicast in each. There's a linked local address in IPv6, and this is really important. It's something that really doesn't exist in IPv4. A linked local address has significance on the link only. So you might have a router with 2 addresses that are the same, and they're linked local. You know, they all start with the prefix FE80, and they're significant only on the link where they're used. The interesting thing about a linked local address is a router should not forward a packet with a linked local source address. So there are applications where it is safe to use packets with linked locals. It is not safe. Excuse me. Caught a terrible cold. There are applications where it's not safe to use a global unicast source. Multicast existed in v4, it also exists in v6. The anycast address is a bit different in v6. There's a formal address type called anycast, but you can't tell an address is anycast by looking at it. And I've also, at first they were called site-like local addresses. Now they're called ULA. And they are almost the same as the 1918 address, but a bit different. A ULA shouldn't be advertised across AESs. They're identifiable because the high order bits point them out as being the ULA. But everybody who uses ULA should allocate a random number for the bits just beyond the high order ones. Excuse me. So let's talk about the next piece of boldness in the IPv6 specification. And that's neighbor discovery and stateless auto discovery. ICMPv6 was a bit different from ICMPv4 in that it had 4 new interesting message types. router solicitation, router advertisements, neighbor solicitation, and neighbor advertisement. With these, you could build two new applications. One is ND. It replaces ARP. So if you want to find out, say, the MAC address of an on-link neighbor, well, in IPv4, you would do that at layer 2 in ARP. In IPv6, what you would do is this neighbor discovery thing. You would send a neighbor solicitation to the broadcast MAC address. And if any of the nodes that receive that neighbor solicitation owns that address, they would respond with their MAC address. So you would now know the mapping of an IP address to a MAC address. Now, the interesting thing is, this moves the function from layer 2 to layer 3. That's actually kind of a bold move, but it was the right thing to do. The reason why is you're trying to learn a layer 3 mapping, the mapping from IPv6 address to MAC address. And to do that at layer 3, it's the right thing to do. Layer 2 should not know that IP exists, whereas it's perfectly okay for layer 3 to know that Ethernet exists underneath it. The next new interesting application is called FLAC. In IPv6, there are two ways that a host can guess an address. One way is with FLAC. What it does is it knows what prefix it belongs to. It's learned that from the router advertisement of its nearest router. Now it needs to pick an address. So it knows the high order bits of its address with the prefix it learned from the router advertisement. It picks a random number, and it then sends a neighbor solicitation to all of its neighbors. If anybody answers saying, yes, I have that address, it knows that it's picked an address that is already in use when it picks another. This is called duplicate address detection. If no one answers, it says, I can use this address, and it starts to use it. Now notice this changed the model a bit. It's gone from being a stateful model, where a node will have the same address forever and always, because either it was statically configured or DHCP server was statically configured and we'll push it on it every time it comes up. But in this case, it's not necessarily the case that a node will have the same IPv6 address every time it comes up. Now, initially, nodes would use their burned-in MAC address as low order bits of their IPv6 address. This was the practice for a long time. Over time, they realized that that kind of has some privacy implications. So people found other ways to pick what the low order bits would be. Pick a random number so you don't have the same low order 48 bits every time they come up. Now, over the years, people developed DHCP-v6. So IPv6 hosts can be configured either way, either statelessly with FLAC or statefully with DHCP-v6. The next piece of boldness is extensibility. A shocking thing is the IPv6 header actually has fewer fields in it than the IPv4 header had. The reason why is when people were designing IPv6, they realized that many fields in the IPv4 header were very seldom used. So they designed an IPv6 header that had only the fields that were used most of the time, and they found this mechanism called extension headers. If you want to add a new field to the IPv6 header, you don't have to bemoan the fact that all the bits in the header are used already. You just add an extension header, and you build a chain. It's called an IPv6 header chain. It's the base header plus its extensions. Now, extensions have to to be processed in the order that they appear in the packet. So the order they appear in the packet is very important. There are basically three classes of extension headers. One is per hop headers. They're processed by every node, and there's exactly one of those, the hop by hop header. There are per segment headers, and there are two flavors of those, destination options of routing. The routing header anticipated the need for traffic engineering. The routing header lists all of the nodes that a packet must visit en route to its destination. So if you want a packet to take a path other than the least cost, you insert a routing header, and in the routing header you have all the nodes that it should visit. Now, let's say you have an instruction that you'd like to deliver to the segment endpoint, to the nodes that are listed in the routing header. You can put a destination options header before the routing header. And because headers are processed in the order that they arrive, the destination options header is processed by every segment endpoint, and then the routing header. Now, there are a few other headers that are processed only at the end of the path, only by the ultimate destination of the packet. That's the fragment header, the authentication header, the ESP, and another destination options header. Fragment is a good example of something that got moved out of the IPv6 header or the IPv4 header and moved into an extension. Why did it get moved out? Well, because very few packets on the internet are fragmented. So it's much better that you put that fragmentation information in an extension only in the packets where it's needed than you have it in the IPv6 header, where 99.99% of the time it's not needed. Okay, at this point I'll pause. Any questions so far?
Any questions?
Oh,
No
okay, I'll
questions.
take that silence as a no.
Yeah.
Okay, thanks a lot. Now, IPv6 was born in a changing world. In 1992, when people first started thinking about IPv6, most IP forwarders were implemented on general purpose processors. Now, there were two flavors of them, complex instruction set processors and reduced instruction set processors. They were both highly programmable, and each was an incremental increase in processing power on the other. But you couldn't process very many packets per second. You could get a lot of programmability, so you could have a new extension header every week if you wanted one. But you couldn't process very many packets per second. Back in the day, I'm trying to remember, in 1995, the fastest networks were running on DS3 backbones. So you were talking about a backbone that ran at 45 megabits per second. You didn't need much more speed than that, much more processor speed than that, because interfaces weren't going much faster. Between 1995 and 1998, you started to see ASIC-based forwarders crop up. They're much less programmable, but they have much more processing power. So around 1998, you started to see networks migrate their backbones from DS3 to OC3 to OC12 to OC48 in about 2000. I think I remember 1999 was the first time I saw an OC48 line card. That had interfaces that went at 2.4 gigabits per second. So, ASICs were getting faster, but less programmable. Now the question is, would this incredibly extensible forwarding plane protocol, IPv6, do well in this new world that was ruled by ASICs? So let's talk about 1999 through 2012. This is just after the dawn, but a pretty gloomy morning. Well, there was minimal economic incentive to deploy the IPv6. classless addressing, private addressing, and NAT all mitigated the effects of IPv6 address exhaustion, but they wouldn't for long. There was minimal customer demand for IPv6. Think about it for a while. What makes a network valuable? Well, the content on it. You know, my network is valuable because I can reach workplace, I can look at CNN with, you know, the content I care about. You know, I can go to Facebook and see how my kids are doing. Well, all the valuable content was on the IPv4 network. Very little of it was on the IPv6 network. So why would any end user want to migrate? The other problem is stakeholders were risk averse after the dot-com bust and the 2001 economic recession. The last thing they wanted to do was take a big risk on a new forwarding plane. Excuse me. So, from 1999 to 2012, we saw very little adoption of IPv6. What we did see is a dizzying array of transition mechanisms. What's a transition mechanism? Well, for a while, we're going to have an IPv4 network with islands of IPv6 emerging in it. Or maybe we'll have an IPv6 network with islands of IPv4 at one time. How do we make the two work together? Well, dual stack is the most comprehensible, and it's what the IETF ultimately recommended. But for those 13 years, we came up with more transition mechanisms than we could understand. Stateless IP, IPMP translation, tunnel brokers, 6RD, transport relay translation, NAT64, DNS64 is a tab, ports for XLEF, DFLite, 4RD, MAP-T, MAP-E, and I apologize to the dozen others that I forgot. Well, this was very bad marketing for IPv6. If you want to deploy something new, especially if it's expensive and it's going to take a lot of operator effort, please make it simple. If there are a million transition mechanisms, we don't know which one to choose, and we don't know how many we need, everybody just runs away. Now, a few of these still make sense. The others can be forgotten. As for the ones that can be forgotten, please use those brain cells to remember your spouse's birthday. Much more important. The next thing we had during those gloomy years were incomplete implementations. And the incomplete implementations had some common bugs, but the bugs were so bad that it made the implementations undeployable. For instance, we had routers, and everybody had bugs. But there were routers that forwarded packets with link local source addresses. Now, if you'll remember, we have some new applications like neighbor discovery, and they assume that neighbor discovery is only going on between two neighbors on a link. You do not want someone off-link injecting ND packets into your link. And the way you prevent that is by using link local source addresses. If routers forward packets with link local source addresses, they have horrible security vulnerabilities. Another problem is hackles would fail in the presence of extension headers. Let's say you had a router that had an ACL that wanted to filter on TCP ports. Well, some applications assumed that the TCP header immediately follows the IP header. This was not true if you had extension headers in between them. And in this case, you could configure an ACL. It would claim to be working, but it wouldn't work in the presence of a packet with an extension header. My favorite was the ND scaling vulnerability, RFC 6583. This is a vulnerability where you could send packets into a network, cause the neighbor cache to get very, very large, memory to exhaust, and you could cause a router to crash. My favorite was somebody demonstrated crashing big carrier-grade routers from his cell phone. The attack device was just a cell phone. Then there were common shortcomings. They weren't a big embarrassing bugs, but they were things that were just left out. For instance, there wasn't feature parity with IPv6. Say, SNMP works on your implementation, but only over IPv4, not over IPv6. There was incomplete Slack support, incomplete support for packets with extension headers. For example, some implementations would just discard every packet with an extension header by default. Others would send them all to the flow path because they couldn't deal with them in the unfast path. Now, in 2012, things started to change. The thing that really caused it to start changing was IPv6 launch day. That was on June 6, 2012. It was a highly promoted event, highly promoted by OPSEC. So, we should all pat ourselves on the back for this. But from that time on, IPv6 traffic levels started to go up. The other thing that happened was just recently, in 2017, IPv6 was promoted to full standard, and that gave it some credit. Another thing that happened was actually a bad thing, but it was good for IPv6. IPv4 address space actually ran out. APNIC ran out in 2011, RIPE in 2012, LACNIC in 2014, ARIN in 2015, APRINIC in 2017. Now, what does that mean? Well, if you can't get new IPv4 address space from your RIR, you've got to buy it. And at the very beginning, address space could be bought at a reasonable price, and there really wasn't a lot of pressure to deploy IPv6. The price has been going up steadily as demand has been going up, and obviously there's no more supply. So as the cost of an IPv4 address goes up, your motivation to deploy IPv6 goes up too. Another thing is IP-enabled cellular phones became ubiquitous. And especially in places like India and China, IPv6 on a cell phone became more and more common. The other thing that happened is popular OS vendors began to ship IPv6, and it's enabled by default. And we'll see what that means in a little bit. Well, in 2019, we start to get critical mass. Today, 28% of the Alexa 1000 websites are reachable via IPv6. These sites attract a large percentage of internet traffic, and the source for that statement is in the link below. The other thing is IPv6 service providers begin to offer IPv6 access to enterprise and residential customers. Excuse me. Google continuously measures IPv6 connectivity among its users, and they've been seeing roughly a 5% year-over-year increase since 2012. Right now, about 30% of its users have IPv6 access. And this brings us to a tipping point. In 2018, Google reports 24 countries where 15% of its traffic is delivered over IPv6. And these are big countries: the United States, Japan, India, Canada, UK, France, and Germany. And 49 countries where 5% of traffic is delivered over IPv6. So IPv6 is no longer a science project. 15% of those 24 countries is a lot of traffic. Now, the other thing we found, a minute ago we said that the Alexa 1000 sites are all starting to become IPv6 enabled. The other thing we said is popular OSs all come with IPv6 all on them and enabled by default. What does that mean? Well, right now, the ISP that delivers service to my house does not deliver IPv6 connectivity. But if they did, the minute they did, 5%, 50% of the traffic in my house would switch instantly from IPv4 to IPv6. So all it takes is one or two big ISPs to offer IPv6, and you get a big jump in the number of IPv6 traffic in that country. So this brings us a little bit to the future. Now, there's a predictable part here. The gradual shift from IPv4 to IPv6 will continue. Many cloud providers already offer IPv6. Many more will become IPv6 ready. When this happens, the other thing that will happen is more and more content providers will offer their content over IPv6. And this will happen as it moves to the cloud. Let's say you have a server in your company's premises. Right now, it's IPv4 only because that's all your ISP gives you. But if you move it to the cloud, most cloud providers are IPv6 ready. So all of a sudden, your content becomes accessible over IPv6. Well, those two bullet points, cloud providers offering IPv6, things moving to the cloud, more residential users are getting IPv6 access. This can only mean one thing. More and more internet traffic will become IPv6. It'll be a very long time until IPv4 goes away. That probably won't happen in our lifetime, but I do predict that IPv6 traffic will be more of the internet's content, or more internet traffic will be IPv6 than IPv4. By the end of our careers. Now, here's the less predictable part. Will IPv6 be deployed as it's specified? IPv4 is a forwarding plane technology. And forwarding planes are based on ASICs these days. That means vendors are going to need to invest in ASICs that are more IPv6 capable. If they do this, IPv6 will be deployed as specified. If they don't do this, what will be deployed is something less than IPv6. What we'll have is some subset of IPv6, or maybe even some mutation of IPv6 that requires less investment in the ASIC. And let's take a look at some case studies where what's deployed is actually less than what was specified. Remember we talked about some substandard implementations where ACLs didn't really work well in the presence of extension headers? Well, operators responded to that by imposing some really draconian filters on packets that included extension headers. There's an RFC, and I forget the number off the top of my head, where somebody did an experiment, and they found that packets that include any extension headers at all are much more likely to be dropped than packets without extension headers. And there was a shocking number. Even a packet with a destination option that's pretty innocent is very likely to be discarded. The reason why is operators put up these draconian filters to compensate for the fact that the ACLs didn't work well in the presence of extension headers. Now that most vendors have fixed their problems with regards to ACLs and extension headers, these draconian filters could be relaxed a little bit. In fact, I encourage somebody who is interested in doing a study about what the filters look like today and how they might be relaxed, because that's someplace where we could get much better IPv6 deployment because we have better implementations these days. Another case study that I'd like to point out is protocols that use one extension header for all purposes, simply because the ASIC is incapable of parsing multiple extension headers. Or maybe it's not incapable, maybe it just can't do it at the same speed, or for some reason, you know, the vendor feels that it's more complex to deal with two extension headers, where you encode everything in one. Well, yeah, you can get your protocols to work, but it's not the IPv6 that was specified way back in 1995. Again, this is an interesting thing for somebody to study. So here we end with a call to action. And what I'd ask everybody to do, especially if you're building protocols around IPv6, is to really grok the IPv6 specification. Now, what does this word grok mean? It means understand what the specs say. Understand why they're saying the things they say. And that really takes a little, you know, it's not a single reading of the specs. It's going through it a few times and thinking about implementations, and maybe even playing with some implementations to realize, oh yeah, the spec says you should do this, and there's a really good reason for it. And then write specs that comply with both the letter and the spirit of the IPv6 specs. You know, when you write a specification for a protocol that runs over IPv6, yes, maybe, you know, there are some places where the spec, where 8200 gives you some wiggle room, but don't take it unless you really, really need to take it. The other interesting thing is to understand and address real ASIC limitations. What is it that an ASIC can do? What is it that it can't do? And how should you adapt to those limitations? There's one graph I'd like to point to your attention. Graph IETF 6-man IPMP limits. It gets a packet and tries to parse the extension headers. Extension headers can be arbitrarily long. You can have like, you know, a 2K extension header, and obviously no ASIC can deal with that. Well, if you hit an extension header you can't deal with, it's a good thing to send an IPMP message back to the source and tell them what the maximum extension header you could deal with would have been. And finally, don't subvert the IPv6 standard to avoid investment in IPv6 capable ASIC. Anyhow, at this point, I will open the floor up to questions.
Anybody has questions?
Okay. Hi. Yeah, Ron, can you hear?
Yes.
Yeah. Hi, Ron. This is Nalini.
Hi, Nalini.
Hi, Ron. Yeah, I have sorry to hear that you're not feeling well, but I have a couple of questions. What would you say the lessons you've learned about protocol development are from working on IPv6 these many years? And a second question is, I have heard that Amazon is buying huge chunks of the v4 address space that's up for sale. Can you talk to that a little bit?
Okay, well the first one I can talk to a lot. What lessons have I learned? The first thing I've learned is IPv6 is really it's a work of engineering artwork. It is scalable and extensible enough to meet everybody's requirements, and I think if we wholeheartedly implement it, if we really get behind it, IPv6 could last us a very, very long time. There are two threats, though. The first threat is wasteful use of IPv6 address space. Once upon a time, I used to think that it was absolutely impossible to run out of IPv6 address space, and we didn't need to be, you know, the least bit restrictive about how we build it out. If somebody wanted a mountain of IPv6 address space, God bless, it's all yours. Jeff Houston set me straight on that. If we allocate IPv6 address space the way we did IPv4 address space at the beginning, that is, give it to anybody who asks for any crazy reason, we will run out. And in fact, we might run out in 25 or 50 years. That's not where we want to be. We want to use IPv6 address space wisely. And then, we might have an IPv6 that will last us for 200 years, and we won't have to go through another transition like this, in our lifetimes or in our children's. The other thing is, IPv6 was designed in a time when forwarding planes were implemented in general purpose processors. It's very easy to change the software that runs the general purpose processor, and adapting to a new extension header or a new feature was no big deal. Back in the beginning, when ASICs first came to be, yes, I realized that there was a problem implementing a full-featured IPv6. Well, ASICs has matured. It is possible to implement a full-featured IPv6 these days, and vendors should not be afraid of doing that. They should embrace IPv6 as opposed to trying to find ways around implementing the full-featured IPv6. Now, granted, there were some things that maybe aren't going to get implemented as we thought they were. The hop-by-hop extension header, well, its role in the world has changed, and maybe it won't get implemented. The fragmentation header, well, yeah, there's no reason to implement that on the fast plane because that's a destination-only thing. But most of the IPv6 forwarding planes, yes, we should invest in doing that. The other thing about the purchase of IPv4 for address space, IPv4 address space, well, first, as a protocol designer, I have very little to say about that because it's policy, it's not protocol. The only thing I can say is once IPv4 address space has been doled out, it's a commodity to be bought and sold. As for who buys it, who sells it, it's really kind of none of my business. It's the same as any other commodity, land or water or hula hoops. I can't speak to who's buying lots, who's selling lots, who has a lot they don't need.
Yeah, no, thanks.
Did I answer the questions? Or?
Yeah, no, thanks so much. I think we're doing good. But I will tell you from my experience, some of the same people who bought huge chunks of IPv4 space in the beginning, they're buying huge chunks, are asking, getting huge chunks of IPv6 space. That's, I know it's a serious game that I know. People are like, how big can I get? Because they saw what it bought in the before world. So they're trying to get as much as they can. Now that's an interesting area. So thank you so much. Drew's
One more question.
Go ahead.
We have some-
I can talk like an economist for a minute.
Sure.
There were two reasons you might buy anything. One reason is because you're going to use it. I bought a pair of shoes last week because I was are you still there?
Yeah. Can you hear?
Hello? Okay.
Hello?
Yeah, there are two reasons you might buy anything. One reason is I bought a pair of shoes last week because I'm wearing them and walking in them now. The other reason you might buy something is you believe it might be scarce in the future. You buy it for investment.
Exactly.
And those are just the rules of economics.
Yeah, no, for sure. People are seeing, they're like thinking, yeah, you tell me this thing is going to last me for years and years. Yeah, right. Well, I'm going to try and get as much as I can now. So, yeah, any other questions?
Yeah, the right thing to do.
Yeah, go ahead, Ron.
Yeah, the right thing to do is allocate address space wisely, so there will never be scarcity, and so that you will never profit off a scarcity of IPv6 address space.
Yeah, sure. Yeah.
Or maybe somebody will profit, but it will be your great-great-grandchildren.
Yeah. No, people, yeah. Well, so thank you so much, Ron. Drew's going to wrap it up.